Hello guys, welcome back, PK here. So in this video, we're going to be evaluating this interesting integral using Feynman's technique, so stay tuned. Okay, here's the question. The question is evaluate this integral I that is from 0 to infinity, then we have e to the power of negative x squared times sine of x squared over x squared, then we have dx. We will be working on this integral using Feynman's technique. So knowing how your sine of x, and it's the same thing as imaginary part of now then e to the power of ix, right? Using this, we can rewrite this integral I. And I is the same thing as the imaginary part of integral from 0 to infinity. Then we should have e to the power of negative x now squared. That times e to the power of ix now squared, of course, over x squared in your denominator. Okay, then I'll be calling this it as integral from 0 to infinity. And we have now then e to the power of negative t x now squared. And then using this product rule of the exponential operation, then we have plus now it x squared over now x squared, and we have now then dx. Okay, so based on this, what we can know is, now note this I of 0. This has to be the real part, right? This is now then the real. Then at the same time, this it is then going to be just the same thing as integral from 0 to infinity. And we should have e to the power of negative t. Negative t times now 1 minus I. Okay, that times now x squared over x squared. Then we have dx. Okay, now if your t is greater than or equal to 0, so for your t is greater than or equal to 0, then we can work on this I prime of t. So if t is greater than or equal to 0, then your I prime of t, this is going to be negative of this 1 minus I. That times integral from 0 to infinity, then we should have now then e to the power of negative t. That times now 1 minus I times x squared, and of course we have dx. Now this integral, this is some Gaussian integral, right? Okay, then let's talk about something useful, right? So this integral from 0 to infinity. And your integrand is now e to the power of, say, negative a, now this x squared, and dx. Okay, the value of this is going to be square root of pi over this 4 times a. But this is only if your real part of the a is now greater than 0. In our case, your a is going to be t times 1 minus now I. Okay, so this, the real part of the a in our case, is now greater than 0, which is equal to now the t. So that's why now we can say this is I prime of the t. Okay, I prime of the t is going to be negative of 1 minus I. Okay, that times now square root of this pi over 4 times now t times 1 minus I. Okay. Then we can actually do a little visual. So let's say this is a complex zone, and then you have this 1 minus I. This is going to be just the same thing as now then square root of the 2 times now e to the power of, okay, then negative pi over 4 times now then I. So that's why using this, we can rework this I prime of the t, right? So let's use this to rewrite this I prime of the t. So I prime of the t is just going to be equal to then negative square root of the 2. That times e to the power of negative pi over 4, now I. Okay, that over, your denominator has to be 2 to the power of 1 over 4. That times e to the power of negative pi over 8 times now I. Okay, then that times your square root of the pi over 2. That times 1 over square root of now then t. Okay, then let's keep working on this, right? So if you keep working on this, it should be the same as now the negative 2 to the power of 1 over 4. Okay, that times e to the power of now then negative pi over 8 times I. That times square root of pi over 2. Okay, that times 1 over square root of now then t. So that's why your I of 1 is equal to I of now then 0. Okay, that plus negative 2 to the power of now 1 over 4. That times e to the power of negative pi over 8i. That times now square root of pi over 2. Okay, that times integral from 0 to 1. Then we should have t to the power of now then negative 1 over 2. And we have dt. Okay, so let's finalize this expression. It should be as now then I of 0. Okay, then we should have negative 2 to the power of 1 over 4. Okay, that times still e to the power of negative pi over 8 times I. Okay, that times now square root of just the pi. Square root of the pi times now t to the power of now 1 over 2 from 0 to 1. So that is why final expression for the I1 is now I0, which is the real part, minus 2 to the power of 1 over 4. Okay, that times now, let me pull the square root of the pi front. And then I'll be making a bracket, right? Okay, then we can use this cosine of now negative pi over 8 plus I times sine of still this negative pi over 8. And then we can close your bracket. Okay, so let's get to the final answer for this integral. So the I is the same as imaginary part of this I of 1. But we just figured this out as now 2 to the power of 1 over 4 times square root of pi times sine of pi over 8. Okay. And then knowing how your square root 2 over 2, this is now cosine of pi over 4. Cosine of pi over 4 is rewritten as 1 minus 2 times sine square of half of this angle, which is pi over now 8. Okay. Okay, so that's why now the sine of pi over 8. This is going to be just equal to square root of 1 minus square root 2 over 2 over 2. Which is then going to be equal to square root of now 2 minus square root of 2 over 2. Okay, so we can get the final answer. So now your integral I is just going to be equal to 2 to the power of negative 3 over 4. Okay, that times now square root of the pi. That times now square root of 2 minus square root of 2. This has to be the final answer for the question. Okay, it's a pretty interesting integral using Feynman's technique, so I'll be back with more questions like this sometime soon.